Hello, everyone. Welcome. Hi, I'm Oliver.
Hi, I'm Lily.
Welcome to Science in Easy English.
Could a supervolcano end humanity?
Right now, as you're sitting there listening to us, the Earth is just, well, it's incredibly restless.
Yeah, it really is.
According to the Smithsonian, there are between 40 and 50 regular volcanoes erupting right now all over the world. But today, we're looking at something way bigger.
So much bigger. I mean, we're diving into a threat that almost defies human comprehension, you know?
Exactly. So for this deep dive, we've got a whole stack of sources for you. We've got USGS commentaries, the official Global Catastrophic Risk Assessment, and some really cool new geology studies.
Right. And our mission here is to just cut straight through all the media hype. We want to figure out what these massive geological beasts actually are, what happened the last time one went off, and if we're actually prepared for the next one.
Because the stakes are literally existential. But, spoiler alert for you, just to keep things from getting too dark right away, there's actually a remarkably high degree of scientific confidence that humanity can and would survive.
Which is a super comforting thought. But before we get into the survival part, we really have to define what we're even talking about because, well, scientists actually hate the word supervolcano.
Okay, let's unpack this. Because I was reading the USGS commentary, and the geologists sound like genuinely annoyed.
Oh, they despise it. Mike Poland, he's the scientist in charge at the Yellowstone Volcano Observatory. He wrote this whole piece breaking down exactly why scientists hate it.
I mean, he called it trite.
Yeah, exactly. He compared it to how people back in the 2000s used to stick the word uber in front of everything. Like, oh, that meal wasn't just delicious, it was uber delicious.
That is such a 2000s throwback.
Right. But he feels like slapping super onto an incredibly complex geological system just reduces an entire field of science to a cheap media catchphrase.
And it's actively misleading for the public, too. Like, when you hear supervolcano, you naturally assume it's just a giant mountain that only does these world-ending massive explosions.
Exactly, and that's just not true. I mean, looking at the data, Yellowstone has actually produced about 80 entirely non-explosive lava flows since its last massive event.
Wait, 80?
Yeah, 80. So it's an active dynamic system, you know? It releases pressure in totally normal, small ways all the time.
Which is why they want to rename them entirely, I guess.
Yeah.
What do the experts actually want us to call them?
They strongly prefer the term caldera systems. A caldera is basically the huge depression left behind when a massive eruption empties the magma chamber so completely that the ground above it literally collapses inward.
Got it. Caldera system.
Right. And to describe the actual size of the eruption itself, they use the Volcanic Explosivity Index, or the VEI scale. They call the really big ones VEI-8 super eruptions.
Wait, I saw in the notes that the VEI scale is logarithmic. Can you just, translate what that actually means in the context of a volcano?
Sure. So logarithmic means that every step up the scale isn't just a little bit bigger, it's 10 times larger than the previous number. So a VEI-4 ejects 10 times more material than a VEI-3.
Okay, that escalates really quickly.
It really does. By the time you get to a VEI-8, you're talking about an eruption that ejects over 1,000 cubic kilometers of volcanic material.
1,000 cubic kilometers. That is just, I can't even visualize that. It's like burying the entire state of Rhode Island under miles of pulverized rock and ash.
It totally defies the imagination. Now, the term supervolcano actually has a surprisingly long history. It was first coined back in a 1949 book review by a volcanologist named F.M. Byers Jr.
Oh, really? Back in 1949?
Yeah, he was referencing this hypothetical ancient peak in Oregon called Mount Multnomah. But the word basically sat dormant for decades until the BBC television program Horizon popularized it in the year 2000.
And the media's just run with it ever since. I mean, I get why geologists prefer caldera system, I really do.
Yeah.
But I have to push back just a little bit here.
Oh, yeah.
Yeah, to me, it's like astronomers getting mad at the term black hole. Like, sure, strictly speaking, it might not be a literal hole in space, but you have to admit the branding is absolutely fantastic for public awareness.
I mean, it definitely grabs your attention.
Right. When you're talking about something that ejects 1,000 cubic kilometers of Earth into the sky, you kind of need a word that commands respect.
The branding definitely works, and whatever label you put on it, the destruction it causes is catastrophically real. To truly understand the risk these systems pose to you today, we have to look back in time to see what they did to our ancestors.
So, looking at our sources, I know the Earth has a pretty violent history, but how often do these massive caldera events actually happen? Are we talking once a million years?
Actually, more frequently than that. The geologic record shows there have been at least 60 super eruptions throughout Earth's history.
Wait, 60?
Yeah, at least. The most recent one was the Oranoe eruption in New Zealand, which happened roughly 25,600 years ago. But the one that really matters for the story of humanity is the eruption of Toba.
Right, Toba. That was in Sumatra, Indonesia, right?
Exactly. That happened about 74,000 years ago. And it is the absolute closest we have ever come to being completely wiped off the map.
I was looking at the estimates for Toba, and it completely dwarfs the New Zealand event. It ejected roughly 2,800 cubic kilometers of material.
Oh, totally. It was so massive that it covered the Indian subcontinent and large parts of Southeast Asia in over 15 centimeters of ash.
Just picture that for a second.
Hmm.
Entire landscapes, entire ecosystems, just suffocated under a heavy gray blanket of glass and rock.
And the immediate physical burial is really only the first phase of the disaster. The real killer is the climate impact. The sheer volume of sulfur gases pumped into the stratosphere creates what we call a volcanic winter.
Because the sulfur blocks the sun, right?
Right, the sulfur dioxide mixes with water vapor to create these sulfuric acid aerosols. They act like tiny mirrors, literally reflecting the sun's radiation back into space. Following Toba, global temperatures dropped by over 10 degrees Celsius.
10 degrees Celsius globally.
Yes, and that sudden, brutal global cooling lasted for a full decade.
That is apocalyptic. Like, on a local level, a 10-degree swing is just a chilly afternoon. But as a global average, that is the difference between a thriving biosphere and a frozen wasteland. It must have just devastated the food chain.
It absolutely did. And this eruption occurred right when early humans were trying to gain a foothold. The environmental stress was so severe that it created a genetic bottleneck.
The human population dropped to fewer than 1,000 individuals globally, right?
Exactly. We were essentially an endangered species.
But here's what I don't understand. If the sun is blocked out, the plants die, and the animals starve, how did those remaining 1,000 humans actually survive? What did they do differently?
What's fascinating here is how the archaeological record answers that exact question. The Global Catastrophic Risk Assessment has high confidence that humans can recover from these events, and they point to a specific ancient site in Ethiopia called Shinfa Metema 1.
Okay, so what did they find there?
They found a dense record of tools, including early evidence of archery and hearths that show people stayed in the area right through the eruption and its aftermath.
But they couldn't just keep hunting the same game if the ecosystem was collapsing.
Exactly. They survived by rapidly shifting their diet. The sudden drop in global temperatures dramatically changed the local rainfall patterns, causing these severe dry conditions.
Oh, I see where this is going.
Yeah, the local rivers shrank from flowing waterways into a series of shallow, isolated waterholes. Instead of starving, these early humans realized that these shallow puddles were essentially traps.
Full of fish, right?
Right, highly concentrated with fish that had nowhere to go. They pivoted to river-based foods to stay alive. They improvised.
That is incredible. So the very drought caused by the volcanic winter actually made fishing incredibly easy for a brief, critical window. It's a testament to how adaptable we are.
That flexibility is absolutely our greatest evolutionary asset. But this raises an important question. We survived Toba, yes. But where are these ticking time bombs located today?
Well, one of the most active threats right now is Campi Flegrei in Italy. It's heavily monitored because the ground there is actively swelling and subsiding, and the human stakes there are just terrifying.
Absolutely. If it erupts, there are 500,000 people living in the immediate red zone.
And the red zone means they're threatened by pyroclastic flows. For anyone unfamiliar, a pyroclastic flow isn't that slow-moving lava you see in Hawaii.
No, not at all.
It's a superheated avalanche of toxic gas and rock moving at hurricane speeds. We're talking temperatures up to 1,472 degrees Fahrenheit.
It's instantly lethal. And beyond that red zone, there are another 800,000 people living in the yellow zone who would be exposed to massive, life-threatening volcanic ash fallout. The weight of that ash alone can collapse roofs and destroy infrastructure.
And then, of course, there's Yellowstone. Our sources highlight some really fascinating recent discoveries there. Scientists have figured out that its next eruption would likely be in the northeast section of the park.
Right, they've been tracking what's happening underground, and the mechanics are complicated. The reports mention deep basaltic melt moving up and heating a pocket of rhyolitic magma.
Okay, can you translate that for us? Why does the type of magma matter?
It matters because of how the different magmas behave. Basaltic magma comes from deep within the Earth's mantle. It is extremely hot and relatively fluid, almost like a thin syrup.
Okay, thin syrup and the rhyolitic stuff.
Rhyolitic magma, on the other hand, is created closer to the surface when the crust melts. It is cooler, incredibly sticky, and packed with trapped gases. Think of it more like thick peanut butter.
Got it.
What's happening under Yellowstone is that the hot, fluid basaltic magma is rising up and literally baking the sticky, gas-rich rhyolitic magma above it.
Which creates a massive pressure cooker. But the annual probability of a super eruption is remarkably low. The numbers show it's calculated at just 6.7 times 10 to the negative fifth power.
Yeah, which translates to a return period of roughly 15,000 years.
So if the magma is actively heating up, why do these systems take tens of thousands of years to actually blow?
To understand why it takes so long, you have to look at the physics of the magma chamber, which the Smithsonian research details beautifully. A normal volcano erupts because pressure builds up inside a rigid rock chamber until the rock fails and it just blows its top.
Like popping a balloon.
Right. But in a caldera system, the magma chamber is so unimaginably massive that the sheer volume of heat actually bakes the surrounding rock for miles. The rock becomes hot and pliable, almost like plastic.
Wait, if the rock is pliable like plastic, how does it eventually snap and erupt? Shouldn't it just keep stretching and expanding indefinitely?
It does stretch for a very long time. That's why the magma can slowly pool without a sudden pressure pop. But it all comes down to buoyancy.
Buoyancy. Like a boat.
Sort of. Over tens of thousands of years, this enormous pool of magma becomes so massive, and it's inherently buoyant because it's lighter than the solid rock around it. It constantly pushes upward against the crust.
Okay, I'm following.
Eventually, the sheer physical upward force of that buoyancy overcomes the structural integrity of the solid rock ceiling above it. The ceiling cracks, depressurizing the chamber instantly and allowing the magma to violently burst out.
Here's where it gets really interesting. Because the mechanism is completely inverted from how we normally think about explosions.
Exactly.
It's not like popping a balloon by squeezing it too hard. It's more like filling a massive swimming pool until the sheer weight and volume of the water just shatters the concrete holding it in. It relies on volume and buoyancy rather than just a quick buildup of gas pressure.
That is a perfect way to visualize it, and that distinction is crucial. Because that slow, methodical buildup, the filling of the pool, is exactly what gives us our greatest advantage as a species today, which is warning time.
Right. Because unlike some existential threats, a supervolcano is not going to just blindside us on a random Tuesday. If you compare it to an astrophysical threat like a gamma ray burst from deep space, that would hit us at the speed of light. Zero warning.
Absolutely zero. But a caldera system, the ground has to swell, the magma has to move, the rock has to heat up. It gives us time.
And our ability to read those warning signs is getting incredibly sophisticated. One of the most exciting developments in the research is a new forecasting technology called the jerk signal.
Yes, the jerk signal. I love the name of this.
It's great, but what is it actually measuring?
It's a highly specialized detection method that scientists tested for 10 straight years at the Piton de la Fournaise volcano on La Réunion Island. It detects incredibly subtle ground movements caused by magma pushing upward into the crust.
How subtle are we talking?
Movements measured in just a few nanometers per second cubed, and a nanometer is 1/1000th of a meter.
That is mind-boggling. But how does moving magma cause a physical jerk in the rock? Is it just friction?
Exactly. Magma isn't water, it's highly viscous rock. As it squeezes through narrow conduits in the crust, it doesn't flow smoothly, it gets stuck, builds up intense local pressure, and then violently lurches forward.
Oh, so it stutters.
Right. And that sudden lurch sends a unique, high-frequency seismic wave, a literal jerk through the surrounding rock. The fact that we have broadband seismometers that can isolate that specific signature from all the other background noise of the Earth is just a massive triumph of engineering.
And the results from that 10-year test period are astonishing. The jerk signal successfully warned of 92% of the eruptions.
Yeah, and sometimes gave authorities up to 8 hours of advance notice.
8 hours is an eternity in emergency management. It's the difference between a successful evacuation and a total tragedy.
And we aren't just looking at standard magma either. Scientists are currently using a network of seismometers to map 3D tremors beneath a volcano in Tanzania called Oldonyo Lengai.
I noticed that specific volcano in the notes because its magma is totally bizarre. It's unusually cool and incredibly fluid, right?
Yes, it erupts a unique type of magma called carbonatite. Unlike the glowing red lava we are used to seeing, carbonatite lava is black, and it erupts at roughly half the temperature of normal lava. Because it is so fluid, mapping its movement in 3D is basically like creating an ultrasound of the Earth's crust. It gives us a much clearer picture of how these complex plumbing systems operate.
All of this monitoring is fantastic for forecasting, sure. But the real question is, can we actually stop an eruption? Because our stack of sources includes a proposal from NASA that reads like pure science fiction. They have theorized a mitigation plan for Yellowstone.
It is an audacious piece of planetary engineering. The idea is to prevent a Yellowstone supereruption by aggressively cooling the magma chamber.
By drilling into it, right?
Not quite into it, but around it. NASA engineers propose drilling massive holes 10 kilometers down into the rocks surrounding the caldera and pumping in cold water under high pressure.
Wow, 10 kilometers.
Yeah. The water would extract heat from the rock and return to the surface at around 350 degrees Celsius. It would slowly bleed off the heat and reduce that buoyancy that we talked about earlier.
So what does this all mean? Because honestly, it sounds absolutely terrifying. I have to admit, reading this, I thought, you are taking a massive industrial drill to a supervolcano. Isn't there an immense, obvious risk that drilling could accidentally trigger the exact VEI-8 eruption we are trying to prevent? It feels like trying to defuse a bomb with a power drill.
It is a totally valid fear, and the researchers definitely acknowledge the risks. However, the plan is meticulously designed to avoid touching the magma chamber itself.
Okay, so they stay far away from the sticky stuff.
Right. The drilling would occur well outside the perimeter of the magma, targeting the surrounding hydrothermal fluids. They would extract the heat from the hot water circulating outside the chamber, allowing the rock to naturally wick the heat away from the magma over time. They would never pierce the actual envelope holding the molten rock.
I see. So it's less like piercing a balloon and more like putting ice packs around the outside of a hot room to slowly cool the air inside.
Exactly. The goal isn't to freeze the volcano solid overnight, but to slowly bleed off enough heat over thousands of years that the magma never reaches that critical, crust-shattering threshold.
That makes a lot more sense.
If we connect this to the bigger picture, the mere fact that we are engineering this kind of solution represents a profound shift in human history.
How so?
For hundreds of thousands of years, from the survivors at Toba all the way to the modern era, humanity has simply been a victim of geology. We reacted, we fled. Now we are shifting from being passive victims to actively engineering our own survival.
We are looking at proactive, planetary scale mitigation. It really puts the scale of human ingenuity right up against the scale of natural destruction.
It does. And it's not just drilling into volcanoes. The Global Catastrophic Risk Assessment details other long-term survival strategies, like global UV sheltering systems to protect agriculture during volcanic winter, and massive emergency food stockpiling. It shows that while the threat is vast, our capacity to prepare for it is growing exponentially.
Which feels like a perfect place to pull all of this together for you. To distill this deep dive down, supervolcanoes or VEI-8 caldera systems are immense, ecosystem-altering threats. They have a terrifying history, and they brought our ancestors to the absolute brink of extinction.
But they operate on massive geological timescales, building up buoyancy over tens of thousands of years. You do not need to lose sleep tonight worrying that Yellowstone is going to erupt tomorrow morning.
Definitely not. Science is watching the magma move in real time. We are mapping the plumbing in 3D, and we are measuring the heartbeat of these systems down to the nanometer. We will see it coming,
We absolutely will.
and we are already thinking about what to do when it happens.
Which brings me to one final mind-bending concept to leave you with today. We talked about NASA's incredibly risky plan to drill into the rock around Yellowstone and pump water to cool the magma.
Right, the drilling plant.
That cooling process would require a massive infrastructure investment and would literally take thousands of years to complete. But think about the thermodynamics of what they are actually proposing. Oh, I see where you're going with this.
Yeah, pumping cold water 10 kilometers deep into superheated rock and bringing the steam back to the surface is the exact definition of a geothermal power plant. Because of the sheer scale of the heat involved, it would generate a staggering, unprecedented amount of geothermal energy.
That is incredible.
So here's something for you to mull over. Could the very geologic monster that currently threatens to wipe out the North American continent eventually be tamed? Could we literally harness a supervolcano to provide clean, unlimited power to the entire continent for thousands of generations to come?
From an engine of mass extinction to the ultimate source of human progress. That is a truly profound thought.
Thanks for taking this journey with us. Keep questioning, keep exploring, and we will catch you on the next deep dive.